Hello, I'm an IB math teacher and today I'm going to show you an IA that I wrote myself. This is the second video of this kind that I'm doing. If you want to watch the other one, I'm going to link it up there. In terms of the math that I used, I believe that this one is a lot simpler, but the point of both videos is the same. I want to make comments about the rubrics so that you can maybe apply some of the comments that I make into your own IA. But most importantly, I think that the part that students find most difficult is in showing personal engagement and reflection. I think those two things are very much connected to each other. And I think that the difficulty in this is that there is no specified set of rules that you need to follow. You just need to show that you're engaged with the content. So let's jump right into this one over here. I really like rockets. I like space stuff. So every time that I watch a video with a rocket launch, there's all this data on the screen, the altitude, the speed. So I decided to collect that data and study it. In terms of personal engagement, this is the first mistake that a lot of people make. I do really like rockets, but I don't need to go on and on about how much I like rockets in order to show my personal engagement. I don't need to write a whole page of backstory about space exploration because that's not what this is about. Personal engagement is about how you connect to the math that you're doing. And hopefully I'll be able to do this in this IA. Let's see how successful I am. And in terms of backstory, really, that's all there is. I just want to contextualize what I'm doing. I don't need to convince anybody that I love this topic. I do also take the opportunity to explain why I chose this particular rocket, the New Shepard. It's because it only goes up and down. It doesn't do horizontal speed. So that simplifies my mathematical analysis. That is an important thing to mention, why you're choosing this one. And really important to give the link to the video where I'm going to collect my data. I have put a screenshot of the video here just to explain like, oh, all of the data is on the screen. So I had the speed, the altitude, and the time. So next, a little description of how I'm going to collect the data. This is about 6-7 minutes of video, so I thought that constant intervals with 4 seconds was going to be enough. But then I also explained that at some parts, like there's nothing happening really, so I use larger intervals. On the other hand, there are more critical parts of the flight where more stuff is happening, so I take shorter intervals over there. It's not a problem. When you're collecting data, you don't have to have your things equally spaced, especially if you're going to be doing regression, which is my plan here. You don't need constant intervals. Anything that looks like a scatter plot is enough. You can do all your data. And also, there is a big limitation in my method for collecting data, and I have to mention that here. I say the intervals won't be exactly constant. This is just because 1 second is really a long period of time, so I do have to rely on myself to click the button at the right time. And of course, in order to be to accept my pause, I only have to be somewhere within that 1 second interval. Sometimes I'm going to click it closer to the beginning of the second, sometimes later, so it's not really even. I am acknowledging that, but honestly, I really don't think it's going to be a problem because the whole thing is 6 or 7 minutes, so it's going to all even out in the end. The point is that it's important to mention that you're aware of the limitations of the processes that you're using. Okay, so here's my table of data. And you guys, it's really not that difficult to make a table that looks pretty for presentation rubric A. I see a lot of bad looking tables. And it's really not that difficult. Like for this type of table, which would be a long, thin vertical table because it only has 2 columns, it's very narrow, but it has a lot of rows because I did pause the video a lot of times. If you don't make it like 3 or 4 or however many you need columns side by side like this, it's just going to look like a big strip. And not only is it going to break across to the next page, which is something that you want to avoid, but also it's just going to be a block of table here and a lot of empty page on the side. That looks horrible, and it's really easy to fix. So I've broken my data into 3 more or less same sized parts. put one next to the other and just pasted it here. It's not that difficult to do. And just like in my previous video about an IA, I am not attempting to be perfect here, okay? I just sat down and wrote this thing for as long as I was having fun, and I did not go to the trouble of making every little thing perfect because some of those things are boring. So let me point out, for example, that the titles of my columns are the units in which these things are measured. So S is seconds and mph is miles per hour. But that's not the full title that the column should have, right? There was a silly mistake on my part. I should have said time in seconds, speed in miles per hour, but there you go. It's done now and I'm not going to change it. Then just plotting the same data as a graph. Like I said, there are so many points that it looks like, it doesn't even look like a scatter plot, right? Because I didn't plot it like a scatter plot. I used the line type of chart in Google Sheets. So it just looks like a function. It's super beautiful. This graph is doing all of the things that you expect it to do if you've ever spent any time thinking about rocket launches. And the text of my IA is going to be about going through all of these things, but let me point them out in the graph while we're looking at it. So this is speed and time. Don't make this mistake. This is not the rocket going up and then going down, okay? This is just the rocket going up because I'm plotting the speed, I'm not plotting the altitude. The point where the rocket really finishes going up and is going to start to go down would be a turning point up here of a graph that we're not looking at. So speed is positive going up, and then speed is 0, and then speed becomes negative. This point here is when the rocket starts to go down. So basically, this is a graph of the going up part. It has a few different stages, clearly different things going on in the graph. So first, it starts at 0, and if you've never watched the rocket launch, just go see the one that I used here. It's really pretty. As soon as the fire starts igniting under the rocket, it doesn't start going up immediately. It burns for a little while before it gets that initial speed. So we are seeing something like this, right? So very concavity up because it's as if it was a parabola that was at the vertex there. So it starts like this because it doesn't pick up speed at once. It takes a little while to start picking up speed. But then it does that, and there's a part here where the speed is increasing kind of constantly. This is a linear function going up. Then something changes around here, and it's still increasing the speed, but it's momentarily increasing slower because the slope of this line is smaller than the previous one, and then it really picks up speed fast until this point up here where suddenly it stops increasing the speed altogether. It's still going up very fast. This is like more than 2,000 miles per hour. This is almost constant speed, like nothing is happening there. And then there is another sudden change here where like the speed just starts dropping really, really linearly. This last part, I think, is the easiest one to understand because it's way up there when the engines turn off. And then the rocket is only subjected to gravity, so that's like a free throw, right? So the acceleration is constant. The gravity is constantly pulling the thing down. So the speed, which is the integral of acceleration, is the integral of a constant, which is a straight line, a linear function. So that's what we're seeing here. Beautiful. That's basically it. That's the IA. Now let's go through what I wrote about this. So this first paragraph here is basically describing that last part, the one that I was just talking about where there's only the gravity acting on the object. And all of the things that I wrote here on the paragraph is what I just said. So for the rest of it, I'm assuming that the force of the rocket engine itself would be a constant force pushing the rocket up. And the reason why that force pushing it up and gravity pushing it down wouldn't add up to a constant force, which would make another straight line, is because as the fuel is burning to make that fire, the mass of the rocket is decreasing, and most of the mass of a rocket is fuel. So that is what makes the problem interesting, is that the thing is huge and it's going to basically burn itself all up until it goes really, really high up. So in other words, I should not expect a straight line if this thing is burning at constant force. I should expect something with positive concavity, because as the mass goes down, the acceleration for the same force increases. And increasing acceleration is the increasing the rate of change of the speed. So that translates into the positive concavity that we see in this part of the graph right here, which is the first one that I'm going to analyze, I think. Yeah, so there it is. I'm focusing on the points from that region. I tried quadratic regression. It was the first thing that occurred to me to try, because basically just because it looked like a parabola. But I wasn't really expecting it to work that well. This is almost perfect. I have a coefficient of determination which is 0.9997. I am aware that the coefficient of determination and quadratic regression is something that technically is only in the syllabus for the AI-HL course, not the other 3 courses, but all of them have linear regression, and this is, trust me, not different at all. It is the same thing. I'm going to make another video just focusing on this topic, so in case you don't know it. But trust me, it's not more difficult than linear regression, so you can use it regardless of which course you're taking. In terms of mathematical communication, please note that both the coefficient of determination and the quadratic function are well typed. Also, please notice that it's okay to just give the results. You're not supposed to explain how to get to it, because this is a technology thing, and you're not going to go, oh, I pushed this button and that button, because that depends on the calculator you're using or what website or software or whatever you're using. It's technology specific how to get it, and that is irrelevant to the IA. The thing is, you know that quadratic regression is a thing that exists. You know that it's the appropriate thing to use at this point. You did it with technology. These are the results. There is no reason to say any more than that about it. Okay, so I just have to say this in order for the things to make sense, but this max Q thing, they explain in every rocket launch video. It's a point of the trajectory in which the rocket is under the most stress, so it's a dangerous point. It makes sense that they wouldn't really be putting the whole force of the engine until after you go through that point. So that really is what you see here. This is max Q. They are taking it easy until they get there, and then after going through that point, constant force, decreasing mass, increasing acceleration until all the fuel is burned. Okay, so I decided to do a little bit extra math at this part after I had already finished recording the video. So this wasn't originally in there while I was talking about all of the other regressions. But the thing is that I was really curious about how come a parabola fits so well there if there was no physical reason to assume that that was a parabola. It was just looking like one. So I decided to go a little bit more into physically what I would expect that function to be. And it ended up being quite interesting in terms of math, and I didn't have to put too much physics into it. So let's go through the highlighted bits in this image. I start with force equals mass times acceleration. I just solve for acceleration, and then I say that the mass of the rocket is not going to be a constant. It starts with a weight that I'm calling b, and then it gets linearly smaller. So b minus ct, where c is time and c is another constant. This is, I'm assuming that it's burning fuel at a constant rate because it's just going as strongly as it possibly can. So then I substitute the b minus ct into the mass that was in the denominator, and I include a minus g there, which is gravity, because the acceleration that depends on the mass of the rocket is pushing up, gravity is pushing the other way, so that's a minus. So I now have this expression for a of t, which is the acceleration with respect to time, and I just integrate that to give what I expect the velocity to be. So it's minus f over c, ln of b minus ct minus gt, and then plus r. That's the plus r is the constant of integration, which I am not forgetting. And then I realized that GeoGebra knows how to do more regression than I knew that it knew how to do. So whenever I learn a new command, I like to write it down in the text of the IA. And that's the highlighted in green part here. That's the command fit in GeoGebra. The list of points, of course, it's those points that I had for regression. And then you can just give him the expression of the function that you want him to fit. I changed all the t's for x's because his independent variable is called x. I changed that minus f over c to another letter called d. Just, I don't know, I thought the expression looked easier this way. And then I just asked him to fit. He found me a value for all of the constants d, b, c, g, and r. That's 5 constants. And I'm going to show you the picture in a minute of what that looks like. But before I do so, notice that the constant c looks like it's 0, which is a very weird thing. First of all, why would he say 0x when he could just say nothing, right? He could just say ln of 5.12. But the thing is that ln of 5.12 is a number, so that would just be a number multiplied by the other number, which is 6,000 and something times x. And then the other part of the expression would be something x plus another number, so that would be a line. And the picture that he was showing me most definitely was not a line. So the thing is that he's saying minus 0x there. He doesn't really mean 0. He just means 0.000 something, and I didn't figure out how to ask him to give me more decimal places there, and I comment that on my IA. So here's another general comment that you can use for anything. If you are aware that you didn't figure out how to do something, you don't have to worry too much about it. It's not like your whole IA is lost just because you didn't figure out how to do this one thing. You just write it down. Like, listen, I know that this is not supposed to be 0. I know that inside of the software it's not 0, but I can't figure out how to tell the software to give me the digits. That is perfectly acceptable, okay? And the other thing that I also comment is that it makes a lot of sense, not for the constant c to be 0, but for it to be very small compared to that b that he said 5.12. Because if b is the mass of the whole rocket, and c is how much mass this rocket is losing per unit of time, it doesn't really matter what unit of time we're using, it's going to be small, right? It's going to be losing a small fraction of its mass. And here are the pictures. This is so beautiful. I just had to include it here. The first picture on the top left, it looks purple, but it's not purple. It's a red function and a blue function, which are pretty much the same. They look exactly the same. So at the first time that I looked at these functions going through those points, I'm like, that doesn't make any sense. I asked him to fit me a logarithmic function. He has a 0 in the expression showing me that it should be a line, and it looks like a parabola? What is going on here? And then first I figured out the thing about the 0 that I already explained here, so it was not a line, but it was still supposed to look like a logarithmic function, but it was looking like a parabola. What is good is that it's looking like the same parabola that I had before. So I started zooming out as far as I needed to make sure that that wasn't a parabola. That wouldn't make any sense for that to just be a parabola. It had to be because I wasn't looking in the correct window to see the logarithmic behavior, right? So that is a very important general comment. If something is not making sense, keep going after it because the math has to make sense. And also, even if you're using technology to plot your functions, you still have to know stuff about functions. You still have to know what you expect the functions to look like so that you can question when you see a graph that came from the technology. You can question whether that makes sense or whether you're required to choose a different window to find the expected behavior. So that's what I started to do. I started to zoom out gradually, and then on the top right, we see the second picture where they already start to separate a little bit. At least now I can see what's red and what's blue. Take a look at the numbers on the axis if you can. I know they're kind of small, but if you can see them, they're getting really, really big. Okay, so I'm having to zoom out an extreme amount. And then I finally see them like separated from each other, but they still look like two parabolas. So I zoom out some more, and then on the third picture, which is the bottom left, I am starting to believe that that left side of the blue function may become an asymptote, which it has to have because logarithmic functions have asymptotes, but I still can't really see it in the third picture. So I zoom out even more to give me the fourth function, which is the bottom right in this picture. And yeah, that blue thing is a vertical asymptote. So I'm satisfied with that. Remember, it was 5.12 minus really small number x. And then when x is equal to something that makes that whole inside of the function be 0, then that's where the asymptote is, because log of 0 is when you're going to have the asymptote, right? Which, come to think of it now, doesn't really make sense, because if it's 5.12 minus something x, then that's going to be equal 0 for a positive value of x. But this vertical asymptote is at a negative value of x. Okay, so remember that 0.000 thing that I couldn't get GeoGebra to tell me the digits of? Apparently it was a negative number, because then it's minus with minus, so it's 5.12 minus something x, and then a negative value of x will make the vertical asymptote that we're seeing here. Now you think that's it? That's not it. Let's remember the physics of what's behind here. The asymptote is when the mass of the rocket is 0, which of course is never going to happen, because even though most of the mass is fuel, it's not all of the mass. But that's what the domains are for, right? I'm not looking at this in a domain for infinity time. I am just looking at a certain period of time. But the point is, if I extrapolate that and think what would happen if the whole rocket really burned itself out and the mass became 0, then I would have an infinite acceleration up, because the mass was in the denominator. It was A equals F over M. So that is something that happens in the future, not in the past. The vertical asymptote should be to the right of my points. This should be backwards. So why is this happening? I didn't even write down this part in the IA, but I'm telling you in the video, because that is not solving the physical equation, right? This is just regression on points. The parabola was already such a good approximation. I don't think I really have a good reason to expect that fitting a logarithmic function would give me the correct logarithmic function. It's just a good approximation, just as much as the parabola, even though there is no reason for that to be a parabola. I hope this is making sense. Regression is an approximation tool. It doesn't necessarily reflect everything of the reality. And the next thing is I want to take a look at this initial part here, because other than that initial part where the rocket is already burning but hasn't really started picking up speed, it looks like two straight lines here, right? I'm not sure if I can correctly draw them on the screen, but do you see there's like something that looks like one straight line here, something that looks like another different straight line here. So I took those points and did linear regression to try to see those lines. There are two lines. There's the purple line, there's the brown line. They are clearly very good in the picture. I didn't even bother to write down Pearson's correlation coefficient because it's clearly very good, as we can see from the picture here. And then there is another one of those rocket thingies. It's called MECO, main engine cutoff, which is the point at the top of our original graph. The rocket has finished burning itself, and then it's not accelerating anymore. So I didn't do another regression for this one because it would just be another line. Oh, I forgot to take the labels of the points here. That's not what I wanted this picture to look like. Not perfect. But if I were to take from point D more or less to J, you can see that it would be another line, right? So that would be repetitive. I don't want to put repetitive things in my IA, so I just didn't. I just said that it's a bit strange because the video mentions MECO happening at 140 seconds, which is here. That also makes sense because from here on down is that main straight down line at the end of our graph. So that makes sense that that's because the rocket is not doing anything anymore at that point. But that also leaves me with the question of what is happening here, right? Because it certainly stopped accelerating quite a few seconds, like 12 seconds before MECO. But I don't think there's anything that I can do with math to solve that question. So I'm just pointing out that, hey, I don't know what this part is. But there is nothing that I can do about it because this is not a flaw in my math. This is like, I don't know enough about the data, and that's fine. This is not an IA about me knowing stuff about rockets. It's an IA about me analyzing data points and doing different sorts of regressions. So that's it. So here's another thing that I mentioned in the beginning of the video. Our going up graph ends with a speed that's slightly negative just after it finished going up and then starting to go down. And then I mentioned here that I stopped there because the video stops. The video starts showing something else. So I don't have the data for after that, which is fine because what they switched to is something that is also interesting because this particular rocket, it has a big part, which is the rocket itself. They call it the booster, and then a capsule on top with the people. So they are attached to each other and then they go up, but when they reach the top, they separate. So the booster comes down first and then the capsule just does a little bit more. So let's focus now on the booster going down after it has separated from the capsule. This is pretty much the same type of table that I showed before. It's again separated in 3 columns so that it doesn't look weird and leaving a lot of blank space on my page. I did the same graph again. Now the speeds are all negative because I'm considering that positive speed is going up, negative speed is going down, okay, and this thing is descending. But look at what's happening here. A straight line going down. A straight line going down is what? Constant acceleration. That's gravity. This thing is in free fall. It's not doing anything. It's just falling. And the interesting thing is that it's not going to turn itself back on for a long time. And it does turn itself back on because it's one of those that land vertically, which is absolutely beautiful. But it only does that here. So I stopped taking data here. What's happening here in the middle is something else entirely. This thing is decelerating on its own. It's not powering itself. It has not opened up a parachute or anything. This is just air resistance. Why wasn't it happening before? Well, because it was out in space. There is no air there. So that was my thinking looking at this picture initially, that this is what should be happening, and then I'm going to look at the points in the data to see if I'm correct. But it certainly looks this way because it doesn't suddenly decelerate. It's a gradual thing, as the atmosphere is also not a barrier, right? There's no air here and then there's air. No, it gradually becomes more dense air that resists against the rocket more and more gradually. So I said, well, it kind of begins happening here. So this is around 360 seconds. So the question that I was asking myself here And pay attention, because this is personal engagement. I looked at this. Personal engagement is not I love rockets. Personal engagement is I looked at this. The curve took a weird turn gradually. I thought maybe this is air resistance. It starts at around 360 seconds. Does that make sense? Where was the rocket at 360 seconds? What altitude? Does that match where atmosphere actually starts existing in around the planet? Let me go look for data on altitudes and atmospheric density and whatnot. This is engagement. It's when you look at a function and it makes you question something else that then leads you to go look for another thing to do. I didn't know that I was going to be looking up altitude, air density when I started doing this thing. It just happened. This is the personal engagement. This is how you show it. It's by actually caring about what you're seeing. Here is that data. Unlike my other tables, this one was not typed by me, like I'm looking at a video, pausing, collecting the numbers. This I copied from a website. So the legend of the table gives the source. This is again one of those things that is so easy to do, and there is no reason for you to not do it. You need to cite your sources. But again, I'm making the same mistakes here where I do not say altitude in feet, I just say feet. And then I just say density without saying the unit of measure of the density, because it was a weird, crazy thing that I didn't understand. And it wouldn't have been fun for me to try to understand it. So I'm trying to have fun. I'm not trying to be perfect. And the S for seconds is actually the time. This is a horrible label for a column, by the way. This is time. It should say time. It's approximate because the altitudes that the website gave me were understandably round numbers, but the numbers that I had in my tables for altitude were all crazy numbers that I was copying from the screen. I didn't put the altitude numbers in the IA because mostly I was just working with the speed, but I did collect them. So I just visually compared those numbers to the ones that I had written down, and I approximated like when did the rocket pass through this altitude. And the 360 seconds that we are interested in is around here. So the next thing that I'm going to do here is that I am going to plot time on the horizontal axis like I've been doing for all the graphs, and then air density in the vertical axis, the dependent variable. I'm not sure what to expect. Let's just look at it. And this is what it looks like. It pretty much confirms what I was thinking. Here is 360. Before that, zero density. So there's no air resistance. The rocket is in free fall. After that, it starts to gradually have some air. And then after that, it goes up and up and up. So the air is going to resist more and more and more, which makes for this positive concavity here, this faster and faster deceleration that we are seeing. I was very happy when this worked. So it's time to try to do a regression for this deceleration part. I'm not going to try a quadratic because it doesn't look like a quadratic. I mean, the obvious reason why it doesn't look like a quadratic, it's because it has a minimum point here, and it looks like it's going to have a maximum point over there, so quadratics don't do that. But there's another reason why I can say that this doesn't look quadratic. It's because the minimum point, which is around here, would be the vertex of the parabola, so it would mean that the axis of symmetry is here, but this doesn't look symmetric to this. So I went to the next one. I did a cubic regression. I put the answer here. Doesn't look very good, to be honest, but the coefficient of determination is big, but whatever. This is not very convincing. And it's totally fine to have a result that is not very convincing. What is not fine is to have this result and just don't care about it. You have to care about it. So if it doesn't look very good, be disappointed. Say that you were disappointed. I said so here, because if you don't care, then you don't have personal engagement. If you don't say that this clearly disappointing result was disappointed, then you're not reflecting upon it. So you're not having rubric D, reflection. You can't just do things and stop. You have to talk about what you're doing. And since I was disappointed about the cubic results, I did go ahead and try degree 4 and then degree 5. But then the results are here and they're horrible. There is no reason why your models should predict that this thing is going to go down here, or this one here is even worse. It goes like this. And this one for the degree 5 actually fits the data like very well on the bottom here. But why does it think it was coming from the bottom? That's just crazy. And then I was pretty much done. This last page that I have on the screen here is just me trying to put a little tiny bit more math into it, because I do feel that although this was a lot of fun, just doing a bunch of regressions is not very challenging mathematically for a student, is it? It's just knowing what the concept is and knowing how to use technology. And there's nothing wrong with that. You can write a good IA with very simple math. I just felt like I wanted to put something more. So I just would mention that I know what differential equations are. So here's one with just gravity. Here is one with gravity plus something else, which I did go look up in physics what's the air resistance should be, and then I went to Wikipedia, but what I found there was that this was going to be way more complicated than I was willing to do in terms of physics, and also a little bit in terms of math, because even this simple one, solving the differential equation, would be outside of the scope of the course. It would be too much. This is already 12 pages. This is an IA. It's over. Don't overthink it. Don't overdo it. Just mentioning here that I didn't type this part. This is an image that I copy pasted from Wikipedia, but that's fine because I am citing my source. You are allowed to use outside stuff. Just don't forget to cite where it came from. So that's it. I hope you liked it. I am obviously very excited about this topic. I'm happy that I did this.